Okay, we are back to clip number 18. Okay, it's a continuation from last time. Okay, we are talking about implementation of the idea of this one. Okay, the general form of production planning under discrete time varying uncertain demand. Okay, last time we already implemented in the Excel format and using open solver to solve for the optimal solution, and then we have illustrated some example of how to extend the problem to solve using the idea of Bender decomposition. Okay, and at the end of the lecture last time we have shown you that we have some the file called Bender PPC uncertain example .m. Okay, that we developed that this program is reading the file input. It's the same problem as we did on the Excel. Okay, but we import the file through the Excel file, okay, to the program, okay, and the program solve, and I already illustrated that they get the same optimal solution, okay. But last time we didn't explain much of the detail of the code, okay. So this time we're going to spend some time to kind of investigate and also look at the detail of the code. Okay, here's the code. Okay, I'm gonna expand the space, the character size for you for better to read it, okay, on your screen. Okay, first, as usual, okay, we clear all the memories. We start solving a new problem, the first line, okay, and then we start to count the time tick. Okay, start measuring, start counting the second of processing from here, and t is now the number similar to the small n in the model. It's the number of period. In this problem we have 12 period, and NSCE coming is an abbreviation of number of scenario. In this case we have 1025 scenario. Therefore, the number of variable, okay, the number of variable here is t plus t is the number of x, right? X1 to x12, okay, and 2 times t times scenario, because we need t constraint, okay, to balance left hand side and right hand side for each scenario, and when you time number of scenario, but for one constraint, okay, in this scenario you need 2 additional variable of I plus and I minus to balance left hand side and right hand side. Therefore NV is the number of variable, M is the number of constraint. The number of constraints, certainly each scenario contain of t constraints, so you have NSCE times t, okay, and we also set n equal to capital T, okay, to fit with the notation that we described earlier, okay. And C is a vector, okay, column vector consists of number of variable and one column here, okay. We initiate with all zeros element, and then this one is from this line to this line, okay. This is the way that we can read the input data from Excel file. First, we identify the file name first, the file name that keep all the data here. In this case, for outside is this one, the test Bender PPC here, okay. Remember that column 1 is column A is DIK, the demand I period I for scenario K for IK. BC, okay, B is H, okay, holding cost, and C is G, okay, which is the I minus per unit I minus cost, okay. So for this one, okay, actually this is the same program as we look at here, okay, but this one have a smaller character, so it's better to explain you down here. Sheet is sheet number 1 because in the Excel file the input data we use sheet 1. Okay, and the range, okay, this is the range of D. Okay, first of all we identify the range. The range of D, if you look at the file here, this is the one. You want the 12 row, okay, from D, column D, okay, here, column D from row 1 to row 12, okay, and then the first C1 to Cn here, okay, the first cost element from the first element to the n element, but not all, because C you look at the C, we already reserve the space of NV, which is equal to the number of variables. But the first n, okay, from 1 to 12, okay, we read XLS read is a import data, okay, from this file name, okay, the sheet number, okay, and D range using this range, okay. This is a command that to import the data from the Excel file. And then for column B, okay, for 12,300, okay, you know this because this is the value of 12 times 20 from 1025 resulting to this. Okay, this is a range of G. Okay, so the range of G we keep at from the C and N plus M. M is a half, the first, we're gonna put from N plus 1 to N plus M, okay. We read the range of H, okay, that's the holding cost for the I plus, and from the N plus M plus 1, okay, to N plus 2 times M, that's the space for the G range, okay. Okay, this one is for I minus, okay, and that's what very easy to understand that we can import all the cost element here, okay. And for the right hand side, okay, B, okay, we just use the B range here which is in the column A, okay. You might remember from this exercise, the column A is a D, the right hand side constant, the demand at period I for scenario K, okay. And this one we identify B range, we just use XLS read, again file name, sheet number, and then identify the range, okay. And that's about it. We can all import the B and the C, okay. And then after this, okay, we just start and doing what we call the Bender decomposition, okay. We're gonna track down but not all line by line, okay, but just give you a detail. The first step, okay, we have the major in the first stage decision value, which is the amount of ordering in each period. That's n period. You remember that small n equal to t. Okay, small n is equal to t. Okay. So this one we have what we call the space for first stage decision variable. How much you're gonna produce or order at period I equal 1 to n. And CV is a cost, okay, for production cost for each period, okay. So CV is we identify CV is the first CJ, the n element of CJ, okay. Remember that CJ have a lot, you also put all the G or the H in C, but CV you reserve for only n element for the cost, variable cost associated to each decision variable in the first stage. And we initialize except j is equal to 80. This one try to make it as similar to what we did here in the Bender decomposition. That you might remember that we start with all the x variable, the initial value is 80, okay. And then okay, after this, okay, we all initialize everything, so we stop counting the time clock. So all the process here to import all the data, and then the initial setup finish here, and now we start to counting the time and measuring the computation times, okay, takes the clocks again, okay. And then we start to have, remember that CX is a cost coefficients, okay, according to the Bender cut model. And if you might remember that the Bender cut always have plus 1 here, because you need to add one more variable in the model. Okay, in this case you might remember that in this model, this is the t. This is an additional variable beyond the 12 variable original variable from the first stage. Okay, so you normally have n, in this case n is equal to n plus 1, 13 decision variable in the sub problem. Okay, so we prepare the dimension for cx, and in the objective function only cx1 is equal to 1 because of the objective function here. Okay, no, objective function of here, that you actually, when you trying to solve the sub problem, you only minimize this one, minimize the cell of t. There's only one decision variable here. So in this program, so only the first variable, which is the t, they have a cost coefficient. The remaining are all 0. Okay, and icon is we count the number of iteration for the Bender. AERR is a duality gap. We initialize as 1. Okay, actually we terminate when AERR is less than or equal to 0.00001, which is around 4 digit precision. Okay, for before termination. Okay, which means that when upper bound, lower bound approaching 0, how close is it 0? When less than 0, when less than or equal to 0.00001. Okay, this is the loop. Okay, that continue, start counting the iteration of the Bender decomposition. The initial upper bound, because we working on the minimization, we set up the very high value for the upper bound, and then if we found a better the lower upper bound, we're gonna replace it. Okay, and this is a cut coefficient constraint. Okay, certainly only t variable. This cut coefficient is a space similar to what we did here. Okay, this is a cut coefficient here. Okay, and as I said, the right hand side cut, okay, certainly start with 0. Okay, and we ix start counting the, and this one is the process to compute what we call dik minus x. Okay, this is for all number of scenario. Okay, we start counting. Okay, we have what we call the d minus initial variable for each scenario. This is for y dual here. Okay, and then we start to compute the d minus, which is the right hand side, which is dik. Now all dik stored in b here. You might remember here from the import program here. Okay, the difference between the demand, okay, with the decision variable x here. Okay, for each scenario I count. After you get the for scenario I, okay, you start computing the cumulative. Okay, if you remember that we need to compute the cumulative value because of the procedure here, the resulting formula that you found in here. Okay, remember this? Okay, you need to find the cumulative, the difference between the right hand side, which now dik, okay, with x star I. Okay, and you need to find the cumulative value. So this is the part that start computing the cumulative value. Okay, start with the cumulative, setting up the space to a variable to store the cumulative, and start with the first one. Okay, with for each scenario I, and for I equal to t. Okay, so we start computing the cumulative of d minus xt. This is d minus xt. Okay, once you compute it, this one use the previous one cumulative plus the current one, and then with this routine you will get the cumulative value of dik minus xj. And then we're gonna check that if this cumulative is greater than 0. If it's greater than 0, you get there's exact formula here, y dual and y dual here. Okay, and then this is not the real dual variable. The real update of dual variable have to be here in this loop, okay, because when we check the d cumulative first, okay, we initially assign the y dual value, but remember, you have to remember that y dual also have a cumulative function also. Start computing backward. So this is just an initialization, except at at t. This is for the initial one, okay, d cumulative at the last period t, okay, you get the y dual immediately, okay, by this formula. If you might remember, you might go to this explain to me. You get at period n, or at the end of the last period of each scenario, you can assign y immediately according to this cumulative value, okay. But for if it's not t is not equal to t, okay, you need to use this condition instead of, because you need to use replacing the y dual by using the next y dual plus g or h minus h, okay. That's according to this one, okay. Once you get the lower bound, upper bound of u, the pick based upon the cumulative coefficient here, okay, you need to plus it with the previous y, the yi plus 1k, okay, to get yik. And with this logic, this is what the program, the routine is all about, okay. And you can see that we trying to reserve, not to save too much memory here, okay, because if you look at the Excel's y, okay, when we compute the y, we will store all the optimum y here, and the cumulative y need to compute here, so it will show all the y here. But when writing in the Matlab code, you can easily, you don't need to keep computing for all scenario first, so you can start doing scenario by scenario and start to accumulate the value, okay. The way we accumulate the value is that once you get the y dual here, okay, certainly the y dual here, okay, for each one of them, you can use this y dual, okay, to compute the cut coefficient here, and with the right hand side at the same time. And when it go to the next iteration, start to with the cumulative formula here, both cut coefficient like that, they will compute the cumulative of y dual and y dual time the d minus xt plus xt, which is now will become the b, the right hand side, okay, because you remember d minus xt is demand, which is the right hand side, minus xt, but now you plus xt, you get the original d, which is the b time y dual, and then this one the cut coefficient, the cumulative of y dual. Remember that this form, this is what we did here in the Excel. In the Excel, it's more illustrative that okay, you want to compute the cumulative y to become the coefficient here, okay. You need to compute the cumulative up to the final here, okay. You want to find the cumulative here and then minus the cost, and then you just move this to become the cost cut constraint coefficients, okay. And but in programming is much easier, and you don't need to compute all the y dual first. You just can do for each scenario, okay, this one. For each scenario, you just start to, okay, find the cumulative of y dual or period t, okay. That's part of cut coefficients. And also the resulting of cut coefficient, once you get all the cumulative value, you just minus the original cost of variable for each t, small t, okay, for t equal 1 to capital T, okay. And the right hand side is the same, okay. You this one, you just use just the original dik, okay, for okay time y dual in each iteration for each scenario, okay. And when this is saving a lot of memory, because when you go to the next iteration, they just replacing with the old. You don't need to separate, showing just like what we did in the Excel, that for each scenario it all show the y. But as a programming, as a coding, you just keep doing for one scenario at a time and using the same variable that reset it, replace it with the new one, and then and use the value to find the cumulative of the coefficient of the cut coefficient for the Bender cut constraint and the right hand side. So this one is setting up, and now you ready to add one more, okay? The constraint you add the next constraint, okay? Certainly the first column have to be -1. This is according to as you know that from the PowerPoint that for the sub problem, okay, you might remember for the sub problem model here, okay, and then the format that linproc whatever that you use in the Matlab, okay, you need to make all inequality as less than or equal. Therefore, for all t here, when they move to the left hand side, it becomes -t, and that's why this has to start with the first column as -1, okay, and all the cut constraint, okay, since this we compute based on the greater than or equal here, so you need to reverse the sign when you move on the other side to make it less than or equal inequality. So this is the logic of this line. And the lower bound, okay, in this case we don't have any restriction for the lower bound, so we setting up that greater than or equal to 0, and this is not better be careful with the first variable. If you're working on some problem that they can allow to have a negative value, this is not the right setup. But just in this case, that is all that all the objective function will never be less than or equal to 0, okay. The right hand side icon, okay, is certainly you need to reverse the sign because you want from the greater than or equal inequality you move to less than or equal inequality. After this, you're ready. You just solve the problem using the linproc. The objective function is cx and cut constraint, okay. Keep adding one at a time, okay, because icon start to increase. So this one is dynamic iteration. After iteration, the size of number of row will be increased 1 as the number of loop increase, okay. And the right hand side, okay, in this case we put the right hand side as a low vector here, okay. So when you default setting by Matlab, so you need to make it column vector, so you make it transpose, and we don't have an equality equation constraint here, so we leave it as a blank bracket, okay, and the lower bound and the upper bound. And then, okay, when you get the result of xs, you remember that the original x will start from x1 will refer to xs number 2, because in the original problem you need to add one more variable, the first variable as a t variable, okay. In according to this objective, the variable t is used as the first variable, so the original x for all 12, okay, need to use xst plus 1. This is to refer back the x, and now we're going to compute I plus and I minus here, okay. This is the most consuming and probably the bottleneck in the for each scenario, okay. We're going to check whether the left hand side and this one when j equal to 1, which means in the first period, okay. If it's not the first period, okay, you need to have an I plus and I minus, okay, which is from the previous period to consider. But for the first period, there's no, you can compare right hand side the right hand side with the decision of xj immediately. But this one, after j is greater than 1, okay, after xj you need to check whether the previous period is there any I plus or is there any I minus, okay, from the previous period according to the constraint, okay. And then you update this to get I plus I minus, and then you start to compute what we call the UV, okay, cost, okay, the cost of adding an u and minus v, okay. And in this case our u is I minus and our v is I plus, okay. So this one we just use the I plus transpose time, this one is the element of h, okay, and I minus, okay, and transpose and time with the cost element and according to g, okay. And certainly based on uniform distribution we're going to divide it by the number of scenarios, and then we check whether the objective function, okay, this is the upper bound, the new upper bound. if, based on the solution found in this iteration. If it's greater than the previous upper bound, and you know that our initial setting of upper bound is a very large value. So very first iteration when they found a solution, okay, they normally replace it with the new upper bound with the current solution, the best solution that they found. And X optimum solution will be keep in the X OPT, okay. And then we found the duality gap, okay, between upper bound and the C. C is resulting from the here, okay. Actually this is T, okay, but we already use capital T in the program. So this is the objective value for after in each iteration of Bender, okay. We check whether this duality gap from the upper bound minus the lower bound, and based on the loop is still greater than not converged, okay. We repeat the process again, finding the, but now you get the new X, okay. So we're gonna start computing d minus xt again, and we get the new y. And so all of this just simulate, okay, what we did here, okay, and put it in the platform of Matlab, okay. That's how this program works. And when we move to the Matlab program with this one, I already show you that we can run this program, okay, and took around 3 seconds, okay. And you know that the number of iteration I showed you last time, okay, is 216. So we got if you go back to the Excel based on the same initial solution, you need to add 216 cut before the solution converge. And you know that the X I showed you last time already that the upper bound value, okay, have to be reaching the same, and also the X optimal solution or transpose is the same as what you get when you solve using the open solver here, okay. Actually this is the solution, okay. So we're going to move on that setting up a new question here, okay, that okay, now we can we can import the problem from Excel, okay, the same, and we check, we already write code here, okay, and we check that we get the same solution here, okay. So we are doing the same thing with what we did in the lecture 1 is that I also write another program here, okay, we call test coding 1, okay. And test coding 1 can also be found in here also, okay, in the lecture 2 folder, okay, on the, which you can have free access to this, okay. This is the same program here, okay, here. But actually what this program did is that they reformulate this problem, okay, of test Bender. This one is exactly the same, that we import the data from the test Bender.ppc Excel file, okay. But now we're going to formulate this problem directly based on this formula, okay, the original formula here, okay. So this code of Matlab here, okay, is after we import all the data here, okay, and then we start to set up AEQ and BEQ here. This is because the original model in here, okay, is all equation here. So this code, okay, just trying to set up the problem directly, okay, according to this model, okay. So you need to have an A times X, okay, the constraint metric on the left hand side, the right hand side, and the cost coefficient of the objective function. And the coefficient of the objective function is already done by the import of C here, okay. We already get with C, okay, C here we identify here C, G and H, okay, C, G and H here, okay. It's all matching up with the parameter here. But now we gonna try to setting up what we call the This is also the right hand side. The BEQ directly become the right hand side by reading the B range. But this one we start to setting up by writing up this as a metric form. Okay, so the left hand side need to write it as a times x consists of x1 to xn and I plus and I minus. Okay, so in this one I'm not gonna explain you word by word, but it's just I want you to go and then try to trace and learn it yourself. Okay, the logic of setting up this is the setting up the matrix of A. Okay, for the first you can see that T. Okay, the first T column, T equal 1 to T, this one is a column 1 to column T, and this one is for the remaining column. For column 1 to column T is according to X here. For the remaining column, okay, will be the cost coefficient. You can see the coefficient we only have 0, 1 and minus 1. Okay, here 0, 1 and minus 1, and that's what the program did. Okay, you can see minus 1, 1, minus. They just put all the coefficient in the right location, and we didn't assign the 0 because at the first place we already declare AEQ here and BQ as a sparse, so especially A. Okay, so whatever the position that we didn't put the value on, they will automatically set that element in the metric is 0, all 0. Okay, so this one I just put the location where it's non-zero, which can be only 1 and minus 1. Okay, so that's the whole idea. Okay, but why the logic? Okay, I want you to track down the program and then study the logic of the program yourself. Okay, and this one also the right hand side that we're gonna use D. Okay, T of S1, okay, as BEQ. Okay, this one is a matching of D. Okay, and actually it's no use here in this program, but just if you want to put the Bender coming in to compare after this direct solving, you can using D. It's better than use BEQ. And also the cost objective function here. Okay, we have C, we have G and H. Okay, but we put all of this in sequence and put it in the vector F here. Okay, and now we are ready to run the program. Okay, we want to put all the production planning solution in variable P with the objective function of Y, and using lin plot, the cost coefficient is F and all equality constant, and you have lower bound as 0. Okay, FLB as a setting here. Okay, let's see. And you can solve this problem to a very large problem because we're using the special command to identify the matrix part of sparse matrix here. They will store only the non-zero element. Okay, which is very little in proportion as compared to the zero element based upon the structure of the problem model. Okay, so this one is a direct solving. Okay, I write this code as you to compare also. This one we already put it in here, and remember that we use Bender over here. We spend around 3 seconds to solve it with 216, and we're gonna take a look at if we use the direct LP solving here. Okay. Okay. Oh, it's even faster. So we don't need any Bender. With only 2 seconds already. That's what I mean. That if you didn't really have a very large scale problem. Okay. Go back to here. If you still have a problem with manageable size, but it's gonna be faster than using OpenSolver solving in Excel, because OpenSolver you need to transform the data of Excel format to the OpenSolver format. That is not directly linked like what we did in the Matlab code. Okay, in the Matlab code we can matching up this to the direct parameter of the lin proc, so they can start to compute immediately. But when you're using the Excel, remember that, or for all the Excel solver, that even though your solver can solve the problem very quick, but you spend a lot of time with the bottleneck of transforming this data spreadsheet format to the mathematical format or the data format that fit with the state-of-the-art software that you use to solve. Okay, that's always a problem with the Excel. Okay, for this one, okay, we show you that it's still faster to solve directly. So for we have show you so far, using Bender is meaningless, isn't it? No, not at all. Because if you go back to the original PowerPoint that I show you, that based on the result that Apisat have done, okay, in this work, when you remember that when we have a small scenario here, okay, we try to expand it to become larger. Look at the table here. When you have only 1,000 or 1,500 scenario, okay, this one is not, the number period is not 12 certainly. Okay, when you have a very few scenario, okay, you can see that when in this case he's using Gurobi, which is the fastest so far in the spreadsheet format. Okay, you can see that Bender took longer time. Okay, when number of scenario is not much. Okay, but Bender have a very slow rate of increasing as the number of scenario increase. Okay, when you from 500 to 10,000, okay, Bender start increasing from 0.34 second to only 2 seconds. But Gurobi, you see that when you solve the direct model, when the number of scenario increase, when the number of variable and constraint increase in the direct model, okay, you see that it took the trend of increment is much more than what you found in Bender. So there's no surprise that when scenario is not that much, where the direct method is outperform Bender. But at one point you're gonna meet what we call the break even. Okay, that you see Bender is very low sensitive. Okay, then have provide too much trend as much as when you're using the direct method. In this case, what he did, he using the Gurobi software. Okay, which is another commercial software. Okay, so what we found here in Matlab is no surprising, but we have to be modify this program, the original Bender PPC, a little bit. That okay, in this case it's fixed too much to only 10,025 scenario. Can we rework on the same problem and setting up that you can have any period? Okay, t can be any value and number of scenario can be any value. And I did that when with the program called Bender PPC set number of scenario here. And you can find that this program also in this lecture 2 folder is here, PPC set number scenario here. Okay, I'm going to open this because it's much better, but this one is in the Microsoft Word compatible. Okay, so this one is a program that modify from the previous program that read the data input from Excel file, but this one is just merging. Okay, you can see the CN here is a cost per unit. Okay, for production for each period 1 to n. Okay, and this one is just this one we also you can change T here, and then but you have to change the format of input here also. But the number scenario here, you can see that we increased to 1 million. Okay, the number of variable over, which is I'm not sure if you gonna code this. I haven't tried yet. Is that to put this setting to the program here to the program test coding. Okay, the test coding also directly with just want to show you that they get the same optimum solution also. We haven't checked it yet. Okay, so we can check it. Why is the optimal solution the same, like 1.0445 with the same. If you might call this one with 1.0244.7, but this one is 0045, which is based on the rounding, it's the same. And also we can check the optimum solution by, okay, since it's stored in P, and also P you want only 12 period, okay, the first 12 period. Okay, so this is the optimal solution of P, of solving this directly and put all the decision variable in P. But the first 12 is actually this, which is actually the same as also as what we found here. Okay, so this one is just checking the compatibility of between you when you're using both software. Okay, and as you see that it means that when you're using the Bender decomposition here, you start seeing that the previous solution is solved, even though you have initial solution as an integer variable. But in the first couple of iterations, it got stuck that it doesn't have to be the integer result. But toward the end, after 216 iteration, okay, it converges to an integer value. But not as always, okay. Let me remind you this. This problem doesn't mean that if you didn't put the integer restriction constraint, all the solution will come out as an integer value. No, not. Because just some case, in some situation, some structure. Okay? So what we can do here is that when we revise the Bender PPC here to this program, okay, and you can here, okay, to this program, you can import, okay, this is all the C, just make a copy from the Excel file, and also here, okay, we can generate here, okay, the amount of PG, and this is the pH. Will you remember PG is the percentage of the G, which is we put it 0.1. This is for I minus, okay, cost per unit, and pH is 1, okay, for the holding cost for I plus, and you know that the corresponding cost coefficient element is just only Cj times Pg, according if it's if this index refer to I minus, okay, when it refer to I plus, or eventually just use this formula. Okay, so this one just generate all the C cost element in the objective function. Okay, and the right hand side, okay, in this one we didn't import anything, we just use the same generation here. Okay, we use the same generation, we use the B generation B round, but because in the Excel what we did here, okay, we cannot use round command from the Matlab directly, because the formula for generation we use integer is mean that after you use random times 50, it's always round down. It's always round down with, to the smallest integer value. So we need to adjust the program a little bit here, okay, to make sure that it works the same as round down. Okay, because in Matlab they have only round, they can either round up or round down, but we have to check whether is it round up, okay, if it's you don't want to round it up, okay, so you need to minus here, okay, once it round. But if it's round down, okay, you just use it directly. Okay, if it's round up, you need to use this formula because you need to minus 1. If it's round down, you can use it directly. So this routine just to make the rounding of generated demand on the right hand side have the same structure as of randomness as what we did in the Excel. Okay, and certainly now this is all, and all the part now is the same here. Okay, but we need to adjust a little bit, okay, for to because just like it here, okay, the right hand side, whatever D minus, this is a different from the previous program that we discussed, okay, and for the generate the right hand side cut here, okay, I encourage you to, because I already explained to you the detail of the previous program, but this one you need to adjust it to fit with the structure of the problem initialization, which is different from what we import from the Excel program, the Excel file. and this one just want to make it general, and the B right hand side can be generate to any scenario, okay, for all you can set the number of scenario as much as you want. Okay, once you get this, okay, so we need to adjust a little bit when we compute, okay, the routine, but using the similar logic, okay, but just adjust the matching of the variable definition that had changed, okay. So all of this is follow the same thing, and also this also happened with the I minus and I plus also, okay. We actually not much, okay, probably pretty much the same with the UV cos and all this one, and update this, okay. So I'm going to show you a little bit, okay, because we already put this program here, numbers in there. In this case we have 1 million. 1 million is a pretty large problem, okay, and it took, I already run it, it took maybe more than 2-3 minutes, okay. So we're not gonna wait that, but we're gonna shrink down to only 10,000, okay, not 10,000, 100,000, let's say. I'm gonna solve 100,000 is already contain more than 1 million decision variable, because for each scenario you have you can say that you have 30 you have 24 variable of I minus and I plus. So your major decision variable just for I plus I minus is already 2,400,000. Okay, and also you need to have another 12 of x1 to x12 as a decision variable. Okay, and the number of constraint is already 1,200,000. Okay, because this is the m. Okay, so it's a million constraint and million variable. Okay, and but I encourage you that to modify this input with this test coding to check whether you get the performance just like what we Apisat did here or not. Okay, and but we're gonna try to run this part for you to see how the results come out. Okay. Sorry. Okay, we should not. Actually, this is the rerun here. We need to run this one. Okay, we only 100,000 scenario. Okay, so we're gonna run it. Okay. So we took very less time to run. Okay. And we also going to observe that when you increase the number of scenarios, what about the number of iterations within the vendor themselves? Okay. Remember that this problem, 2 million something number of decision variable and more than 1 million constraint. Okay. And I'm sure that when you're setting up using that structure problem with test coding, you're going to find some problem. Okay, when you run it. And it's gonna take more time than what we have here, but this one is keep going. Okay, around 37-38 seconds. Okay, 37-38. Let's just say that if you increase number of scenario 10, okay, to become 1 million, which is 10 times. Okay, if you use 10 times this, it's gonna approximately 5 minutes something. Okay, to solve for the 1 million. Okay, we're gonna observe what is the C opt. Okay, which is the optimal solution. Oh, sorry, different one. It should be X opt, okay, transpose, okay, which is a little bit different, right? This 38, but in this one you get in the original problem when you solve, you get 39 here. Okay, but the trend almost equal for each other. Okay, and what is the upper bound here? The best solution. It become 1.0029. Okay, remember that when we solve for the 1025 scenario, okay, 1025, you get 10244. Okay, 10244. But when you dealing with a million, the 100,000, you get 10229. Okay, if you have which one you have more confident, I have to say this, right? Because this one have you solving with more but the first 4 digit is already equal to 1022, right? This one time 10 to the 4, okay? But just the 5th digit. But you can see that this one is more believable because they experiment with a more sample of the scenario, more number of scenario. Okay, we might try for the 10,000. Okay, we might try for 10,000. We run it again. Okay, for 10,000. It's gonna be very quick. Okay. Oh, we forgot to monitor the icon. Only 6 seconds. Okay, we check the upper bound again. This one is what 1.0225. Okay, pretty similar. Okay, close to this value. This one 244. Okay, but this one is 225. Okay, the previous one is 229. Okay. Oh, but this one is too much already. We're not gonna go back. But we're gonna take a look at the number of iteration which count by icon. So the number of cut is 210. Remember that how much what we did in this example? 218, right? If you might remember, 200 something also. So even though you increase the number of scenario, the number of bender cut, the same problem doesn't differentiate that much. Okay. And the same if you monitor when in case of 100,000 or even 1 million, you're gonna get 200 something also. Try it, okay? If the program is there already. And also you can try to adjust to make this problem input, okay, to the test coding, okay, to check whether how far this direct model can go, okay, when using the same computer. Okay. So in this part, that's just about to wraps up all the Matlab program that explanation of all the Matlab program that we developed to solve this type of according to the problem here. Okay, and also we didn't conduct the experiment here, but we gave you all the tools, okay, in the Matlab code, and also as you say in the Excel code, if you be able to develop the VBA, okay, macro, it would be interesting to compare between two platforms also. Okay, you might wonder that, okay, everything seems to be fit within themselves, but how much you can do out of this? Okay, so what should be the homework, and then what should be what we can do about what we already have in here. Okay, so next time, okay, in the next script we'll go back and we're gonna go to more detail about these two papers of Wagner and Wittin, which is the original one, and the work of Apisak and me that is extended under the uncertain demand. Okay, we're gonna go back and read and then summarize the content of these two papers, and also we will see some of the open question from what we already studied so far, and what we can do more about it. And there's some part have nothing to do with go back to the original paper of Dan 6 here also. Okay, so Dan 6 still not going far away. Remember that we start the lecture in this part by looking at the example 3 here, okay, as a starting point. Okay, you might go back and look at example 3 and is there any similarity and is there any different from what we study here in this module here? Certainly there's something different. Okay, and with that different, can the approach that we already told you about this formula be applied to the to handle those differentiation? Okay, so from now on in this part, I'm gonna close it here, okay, and let you go back and study all the Matlab code and the existing file of the Excel, and then see you in the next script. Okay, in the next script.